Okay, today we are going to learn about the extended real number system. To introduce the system, we start off with some sequences of real numbers which are not convergent. We know we have already seen what a convergent sequence means, and we have also proved many results which allow us to detect convergence or lack thereof. So let's look at this example first. This is the sequence of all positive integers. Now we know from our previous results that this sequence is not convergent. The result that helps us ascertain that is that every convergent sequence should be bounded. But this is not a bounded sequence, so it cannot be convergent. Now, in spite of this non-convergence, or rather we should say divergence, we feel intuitively that since the terms of this sequence are increasing without any bound, so this sequence should be converging to plus infinity. This is just a vague notion. Okay, here the word converging does not mean the convergence that we have already come across in the previous section. That is because plus infinity is not a real number. Now we feel that this sequence should be converging to plus infinity in some sort of an extended world of which plus infinity is a part. Okay, in the real number system there is no plus infinity. So that's what we feel, that is our intuition. Just like that, this second sequence, which is the sequence of all negative integers, that is also not convergent in the ordinary sense to any real number, because just like this one, this is also not bounded, but again we feel that it should be converging to minus infinity. This also is not a real number, so this is only our feeling, our intuition. Apart from these two things, we also have that kind of sequence where the terms alternate between some values, some two values, 1 and minus 1 in this case. This sequence is also not convergent in the usual sense of the word convergence. The reason is different because one more result from the previous section tells us that every convergent sequence should be a Cauchy sequence. Now, unlike these sequences, this is a bounded sequence. So, using boundedness, we cannot decide divergence. Instead, this is not a Cauchy sequence. It is, for example, not eventually 1 by 2 steady. No matter how many terms you remove from the front of the sequence, what you are left with, there you will always get 1 and minus 1. The difference between any two such terms, the numerical difference is 2, which is not less than or equal to 1 by 2. So this sequence is not a Cauchy sequence, and as a result it's not convergent. But unlike these two sequences, we don't feel that this is say converging towards, it should converge towards plus infinity or it should converge to minus infinity. This exhibits a different kind of behavior than these two. Although we will see in one of the coming sections, I think the next section itself, I am not sure, I don't remember correctly, that in this sequence, these real numbers 1 and minus 1 are limit points, which is a concept we will come across. It's something entirely different from these things. Another example is this. This shows a behavior different from these three. It's not convergent, okay, because it's not bounded. Just like this two, it's not bounded. But unlike these two, this should not, we don't feel it should entirely converge to plus infinity, because part of it you can say very vaguely, since these are just vague things that we feel should be true in some extended world which includes the system of real numbers as a part of it. So we can say that half of the sequence is going towards plus infinity and the other half is going towards minus infinity. So in the usual sense, this sequence is should neither converge to plus infinity nor minus infinity. At the same time, this is not bounded, so it's not like that one. To make sense of all these things, we make plus infinity and minus infinity part of we consider these two as also some objects. We attach them to the system of real numbers and we get a larger system than the system of real numbers. That is the extended real number system. So that is formally presented in this definition. So this is the first definition of this section, 6 to 1, and it's naturally named extended real number system. The definition is simple enough. It's just simply that you attach these two things, these two objects to the system of real numbers. What you get is the extended real number system. So the author has written it in this way. The extended real number system we are going to denote it R star. Okay, is the real line R along with two additional elements. Attached, plus infinity and minus infinity. Some people don't use the plus sign before infinity, but I think that is not correct. In the sense we are going to treat these symbols, we should put plus sign. Okay, so plus infinity and minus infinity. These elements means these two things are distinct from each other and are also distinct from every real number. Note that this second part of the definition tells us what this equality relation is in this extended set. So according to our definition, R star is actually nothing but this set. Okay, and the equality relation on this larger set is defined like this. On R, equality means what we usually mean. Okay, and if you have an ordinary real number x, then x is never equal to minus infinity. At the same time, x is never equal to plus infinity, and minus infinity is also different from plus infinity. By the way, do you remember the definition of equality of two elements in R? If you really go to the construction of real numbers, then a real number is defined to be the formal limit of a Cauchy sequence of rational numbers. So when you say x is a real number and y is another real number, then x is the formal limit of some sequence an, where an is the Cauchy sequence of rational numbers, and just like that, y is the formal limit of some Cauchy sequence bn of rational numbers. Now we say that x and y are equal when the sequences an and bn are equivalent to each other. We already have seen the definition of equivalence of two sequences. Okay, so in this second part, we are just simply saying that these two symbols are different from each other, and also they are different from all the real numbers. So that's what we are saying in this part. What else is there in this definition? The third part of the definition is this. An extended real number x. Let me first write the sentence and then we will try to understand what it means. Is called finite if x belongs to R. And is called infinite if either x is minus infinity or x is plus infinity. The definition does not explicitly say what an extended real number is, but you can sort of understand that an extended real number x is any element of this set R star. If you take an arbitrary element of R star, that will be called an extended real number. Now such a number is called finite if it is an ordinary real number. Otherwise, it is of course either minus infinity or plus infinity. In these two cases, we say that the extended real number x is infinite. And there is a remark also. this definition is not directly related to the notion of finite and infinite. That we saw in section 3.6, where which is about finite sets. There you recall we have already defined what a finite set and an infinite set means. Now this notion of plus and minus infinity, they are not directly related to that notion, although the concepts are similar. Infinite sets in section 3.6, although it is of course similar in spirit. Calling an extended real number finite or infinite, that's what we are talking about that. Okay, that is not directly related to calling a set finite or infinite. Okay, now fine. So we have two new symbols. So what? So far what we don't have much in this extended system. We just have two new symbols and we have a way of deciding when any two extended real numbers are equal and when they are not equal. Okay, now we want to put some more structure to this set by introducing some more operations, but at the same time we have to be somewhat cautious in doing so. The reasons will become apparent very soon. So the author writes, these new symbols minus infinity and plus infinity at present do not have much meaning. And the reason is that since we have no operations to manipulate them, except of course that condition for equality. Except equality and inequality. So now next we are going to place a few operations. The first one we are going to do is negation. That is when you have an ordinary real number x, you know what minus x is, and we have in fact defined it rigorously, and we have seen that minus x is also a real number which has certain properties. For example, when you add x and minus x in taking them in any order, you get the real number 0, things like that. So we want to define some sort of negation of an extended real number, just like ordinary real number. So that we are now going to do in this. But before that, let us just, since we are writing everything, so let's write this also. Now we place a few operations on the extended real number system. So this is negation of extended reals. The operation, this is how the author writes it. Operation of negation, which takes every real number to its additive inverse, in, or should I write on, the ordinary system of real numbers is extended to the larger system R star by defining. So we just need part of R star is R, so only two elements are new, so we need to define their negation, that's all. And you can almost guess what we are going to do. The negation of plus infinity is defined to be minus infinity, and the negation of minus infinity is defined to be equal to plus infinity. Okay, so now we have minus for every extended real number. We already had minuses for ordinary real numbers, but now we have them for these two new symbols also. Thus, every extended real number x has a negation. We call minus x also a negation. Negation is the operation as well as the element that we get after negating something. And this this law that we got previously for ordinary real numbers is also true in this extended system. You can easily verify. You just have to verify it in only two cases, when x is plus infinity and when x is minus infinity, which I leave to you. It's very easy. Okay, now having defined all these things, the next natural thing we want to do to this extended system is we want to extend the ordinary order relation that we have on the system of real numbers, that is, which allows us to say which real number is less than which real number, that thing. Okay, so that comes in the next definition. Ordering of extended reals. And the definition goes like this. Let x, y be two extended real numbers. We define this i.e. x is less than or equal to y if one of the following conditions is true. The first condition is that it may happen that x and y are ordinary real numbers. If, okay, since we are writing this as conditions, so they are statements. X and y are ordinary real numbers and x is less than or equal to y as real numbers. As real numbers, we already know when we should have this, or when what it means. So when that happens, then we also say that the extended real numbers x and y are in this relation to each other. X is less than or equal to y as extended reals also. Condition B is y is equal to plus infinity, and condition C is x is equal to minus infinity. If y is plus infinity, then irrespective of what x is, x will be less than or equal to y. Just like that, if x is minus infinity, then for any extended real y, we define x to be less than or equal to y. Don't forget that this is a definition, this is not a result. Okay. And besides this, we say that x is less than y if usual thing x is less than or equal to y and x is not equal to y. We say means we are defining this, okay, This symbol means x is less than or equal to y as two extended reals according to this definition, and at the same time as extended reals they are not equal. When this happens, we express these two things at once by writing this. And just like that, there is of course that other way of writing the same thing. We sometimes write y greater than x instead of x less than y, and y greater than or equal to x instead of x less than or equal to y. And then there is a small example illustrating these things. This is example 4. Three is less than or equal to 5. These two extended real numbers are actually real numbers, and in the smaller system of real numbers we already know that 3 is less than or equal to 5. So by part A of this definition, of the previous definition, as extended reals also 3 is less than or equal to 5. Like that, 3 is strictly less than plus infinity. Okay, let's see why. When we see something like this, we should not feel that, okay, I feel it's true, so it is true. No, you have to, in mathematics that should not be. Of course, when you are going to formulate something mathematically, then that type of intuition can be useful. But once you have formulated a notion rigorously using some sort of mathematical definition, then every time you see such a thing, you have to go back to the definition and see exactly what is happening. 3 is less than plus infinity because according to this definition, if you think of 3 in place of x and y in place of plus infinity, then because y is plus infinity, x is less than or equal to y. So 3 is less than or equal to plus infinity. That is the first thing. And the second thing is 3 is not equal to plus infinity. That also comes from our definition of the system of extended reals itself, where we say that plus infinity and minus infinity are distinct from each other, and also none of them is equal to any real number. So from there we are getting these two things, and that's why we are writing 3 less than plus infinity. Then continuing like this, and like that, minus infinity is also less than plus infinity, but 3 is not less than or equal to minus infinity. Okay, for these things you figure these things out. Okay, now fine, we have defined the extended real number system, and we have also defined an ordered relation on this system. Now what are the properties of this ordered relation? It will be nice if this ordered relation has properties similar to the ordinary ordered relation that we have in the system of real numbers, because you see what our journey started from the system of natural numbers, and then we moved to the larger system of integers, system of rational numbers, the system of real numbers, and now we have defined a slightly larger system. Every time we transition from one system to a larger system, we try to bring all the things that we already had in the previous system to this, and then something else. In particular, in all these things, we had this order relation, which we continued to have. I mean, we extended the scope of this to the system of integers, and then from there to rationals, then to reals, and now we have done that to extended reals also. But in each such transition, we have seen that the basic properties of see, all these relations, although we are denoting them by the same symbol, strictly speaking they are different relations, because the elements that they relate or don't relate are different. Every integer is not a natural number, every rational number is not an integer, and every real number is not a rational number. So these are actually different relations, but in spite of being different, they have similar properties. All these relations are ordered relations. They are all reflexive, they are all antisymmetric, and they are all transitive. So it will be nice that the new definition also has those properties, and it turns out that it has. And for that we have this proposition. So let x, y, and z be extended real numbers. Then the following statements are true. Reflexivity. This statement says, you already know what it says, x is less than or equal to x. X is related to itself by this relation. Keep in mind, now x is not necessarily a real number. X can be plus infinity or minus infinity also. And this relation is also not our ordinary order relation, it's determined by this definition. Then antisymmetry. If x is less than or equal to y and y is less than or equal to x, then x is equal to y, and then transitivity is also true. Oh, this is not how things are given in the text. Okay. Instead of they are saying it at once. We will see later that any relation satisfying reflexivity, antisymmetry and transitivity is called a partial order relation. The order relations we have been getting so far are, besides being partial order, they are total order. Any two elements can be I think it's premature to say these things. Let's just see what Professor Tao has given. After reflexivity, we have trichotomy. Exactly one of these following statements is true. X less than y, x equal to y, x greater than y. Okay, law of trichotomy. And then we have transitivity. So what I said about partial order and total order, let's just forget that for the time being. We will see those things when the time is when the time comes. Transitivity. If x is less than or equal to y and y is less than or equal to z, then x is less than or equal to z. And since we also have negation of extended reals, so we have that familiar thing that when you in the system of real numbers, we say it like this: multiplying by a negative real number reverses an inequality. Here we don't have multiplication, but we have negation. So the next thing is negation reverses an inequality, or reverses order. The meaning is saying if x is less than or equal to y, then minus y is less than or equal to minus x. Or if you want to keep on writing x on this side, then minus x is greater than or equal to minus y. So there you can see the inversion. The proof of this is, of course, by now you know how things are in this book, is the first exercise. So that means when we solve these exercises, we will prove it. Okay, so let us move on. Okay, now the next natural thing one would try to do is bring the other operations also, because we have been doing that, no? And we have been so far trying to bring whatever we had in the previous system, everything to the next system, and then something extra. Unfortunately, that cannot be done in a very satisfying manner here. We have a way of saying when extended real numbers are equal or not equal, and more than that, we have a way of saying when one extended real is less than another extended real. So the next natural thing to do is to bring the algebraic operations, addition, multiplication to the extended reals. But here is the problem. One could also introduce other operations on the extended real number system. Such as addition, multiplication, etc. However, this is somewhat dangerous. As these operations will almost certainly not obey the usual rules of algebra. So far they have been obeying, but now we have sort of hit a dead end, so to speak. For instance, how the author writes, we feel it reasonable, we seem that it's reasonable to define, okay, it feels reasonable given one's intuition of infinity. To define this, you add 5 to plus infinity, you feel that it should be plus infinity, and just like that you add 3 to plus infinity, it should be plus infinity. Intuition of infinity is just that infinity is infinitely larger than, I mean, it is something which represents, I mean, you see, you think of ordinary numbers, because we have 5 and 3 here, you think of them as cardinalities of sets, that is numbers which represent sizes of sets. So 5 represents 5 number of some things, okay, a set having 5 elements. 3 represents a set having 3 elements. Now if you take the union of a 5-element set with an infinite set, then the result is an infinite set. So from that this intuition comes. It's like adding a drop of water to an ocean. Nothing changes, essentially nothing changes. It's like that. Okay, so if one defines things like this using our intuition, it seems intuitive enough that this is how the definition should be. But then plus infinity plus 5 is equal to plus infinity plus 3, while 5 is not equal to 3. So cancellation law, with which we are so familiar and which we keep on using every now and then, it breaks down. Okay, cancellation law is no longer true. So things like the cancellation laws or cancellation law breaks down. So if you want to define, of course you can define, but then in that extended system, results start to break down. Okay, they are no longer true. You cannot extend everything. So it's not a situation like transitioning from Q to R. Whatever we had in Q continued to be true in R, and in R something extra is also true, the least upper bound property. But in this transition, that is not the case at all. Okay, we forget about the properties. We are failing to define ordinary algebraic operations also consistently. Breaks down if we involve infinity, and that's why we will not do it. To avoid these issues, we will simply not define any algebraic operation on the extended real number system, except of course negation. We have already done that. And order we have defined. Okay, now because we have order relation on the extended real numbers, which behave just like the ordinary order on the ordinary system of real numbers, still reflexivity is true, trichotomy is true, transitivity is true, and also negation reverses order. Okay, so the next step then is to define supremum of sets in this extended system, just like we did for the real number system. So that is the next definition. supremum of sets of extended reals. Let E be a subset of the set of extended real numbers. We define the supremum notation is also like what we already have for subsets of real number system. So E also called the least upper bound of E as follows. If E happens to be a subset of the ordinary real numbers, it may happen, then supremum of E is as defined, in our previous definition of supremum, the number is definition 5510. Let us recall that definition. Okay, if E is empty, is the empty, sorry, I'm stammering, I don't know why. If E is the empty set, then its supremum is defined to be minus infinity. If E is a non-empty set and is not bounded from above, then its supremum is defined to be plus infinity. And if E is a non-empty set that also is bounded from above, then we have our theorem which says that there is a least upper bound, and that least upper bound is by definition the supremum. If you go to definition 5510, there you see these things. And supremum of E is plus infinity when E is non-empty and not bounded above. There we mentioned in that definition that for now these symbols have no meaning, but now they will have meaning. In this extended system, the supremum that we will define will match with these things. Okay, and everything will fall in place when we, after this definition, there is a result also which says that here also in this extended system, supremum of E behaves like what we have what we had previously. That is, it is actually the least upper bound. It is the least among all the upper bounds. So this is one part. Then if plus infinity is an element in E, then we define supremum of E to be equal to plus infinity. And there is another one, if plus infinity does not belong to E but minus infinity belongs to E, then we define supremum of E to be the supremum of this set. Note that in this third case, plus infinity is not there in E, but it has minus infinity. So if you remove minus infinity from E, then this becomes a subset of the ordinary set of real numbers. So this last thing, supremum of this falls under the case A, okay, because it's an ordinary set of real numbers. So this part of the definition applies, and these are all the possible cases. Now, based on this notion of supremum, we can define infimum. We also define the infimum also known as the greatest lower bound of E by the formula. Infimum of E is, by definition, the negation of the supremum of minus E, where minus E is defined to be the set of the negations of all the elements of E. Note that although we will likely be dealing with plus and minus infinity, but because we have negation, that operation is already there in the system of extended reals, so there is no problem. And I think there are a few examples illustrating this concept before we get to that result. So this is example 7. Let me write it there. Let E be the set of all negative integers and minus infinity. Okay. Then supremum of E, according to our definition, part C is applicable. E does not have plus infinity and minus infinity is there in E. So according to our definition, we should calculate this, which is nothing but the supremum of the set of all negative integers, and you can clearly see that this is -1. Now because we have supremum, we can calculate the infimum also. Okay, to make things extra clear, let's first calculate -e. Note that -e. So to calculate -e, you can see the definition. We just have to negate all the elements. So negating all the negative integers gives us all the positive integers. And negating -infinity gives us +infinity by that definition, by the definition of negation. Okay. So supremum of -e will be what? Now here part B of the definition of supremum applies, because -e is a set which has +infinity. So by definition supremum is +infinity, which implies the infimum of our original set E, which by definition is the negation of the supremum of -e, is the negation of +infinity. So this is equal to -infinity, which makes sense also, because -infinity is the smallest element of E. In that sense, it should be the infimum. I mean, in our intuition, it should be the infimum, and according to our definitions and all the things, it is the infimum. Okay, so then there is another example. The set there is one more element also. 0.9 has supremum 1 and infimum 0.9. Here the infimum belongs to the set but the supremum does not. But in spite of not belonging to the set, the supremum is in some sense touching the set. from right hand side, from the right. How does tau write it? From the right. And then there is another example. Note that the supremum of the empty set is minus infinity, and we don't even have to follow the new definition, because this is a case we saw in the old definition also, 5510. This is minus infinity, and okay, what is infimum of the empty set? If we apply our definition, this is the negation of the supremum of minus of empty set. Now the empty set has nothing, so by the definition of negation of a set minus E, that is also empty. And this is minus infinity, so this is plus infinity. So in this strange case, the supremum is strictly less than the infimum. Note that supremum of the empty set is strictly less than the infimum of the empty set, and this is the only situation, this is the only subset of the extended real numbers in which this happens. In all other sets which are non-empty, infimum is less than or equal to supremum. Exactly why, that we will see in the result towards which we are going. Now before we get to that result, actually there is a fantastic way of intuitively understanding all these things. I mean the supremum and infimum of a set which is a subset of the extended reals. And professor writes it like this. One can intuitively think of the supremum as follows. Imagine the real line with plus infinity somehow on the far right. And minus infinity on the far left. Let us draw it here. And let's do it nicely. Okay, so we have plus infinity here and minus infinity here. This is the real line which extends indefinitely on either side. Imagine a piston at plus infinity moving leftward. Moving leftward until it is stopped by the presence of a set E. The location where it stops is the supremum of E. So you can think of a piston like this. Okay, I'm not really sure how an actual piston looks, but it looks something like this. It has a cylindrical shape and it is attached to some sort of handle on one side. So it is moving from, its motion is leftward. It is coming from plus infinity. Now this will stop here somewhere. Our set E is there. The moment it encounters E, it will stop there. That is the supremum of E. So it's like this. Okay, so this is the supremum of E. Say there was some sort of collision which made it stop. The collision with E, that is where supremum of E is. Just like that, you can think of another piston at minus infinity moving rightward. When it encounters E for the first time, it stops there. That is the infimum of E. It does not feel like a very nice way of I mean, it is very natural, but why suddenly pistons? But you will see that it is nice, and I feel it's really fantastic because of this reason. Anyway, let's just complete the writing. Similarly, if one imagines a piston at minus infinity moving rightward and stopping only when it encounters E. Okay, I have changed the language a little bit. The location where it stops is the infimum of E. Okay, fine, this is very natural, but what happens when E is empty? When there is nothing in E to stop these pistons, the pistons will continue their journey, will phase through each other because they are stopped only by E, not by themselves. Okay, will phase through each other. This piston will land at minus infinity and this one will land at plus infinity. So according to our intuition, the infimum of the empty set should be plus infinity and the supremum of the empty set should be minus infinity. In the case E equal to empty set, the pistons pass through each other. We should understand that these pistons are moving on the real line. Okay, so they have to come together and they will phase through each other. The supremum landing at minus infinity and the infimum landing at plus. This is a very nice way of thinking about this whole thing. I mean, which also includes that strange, that's why I said it's fantastic. It also includes that strange case where which is the only case where supremum is less than the infimum. Okay, now finally we have that result which justifies calling these things least upper bound and greatest lower bound. Okay, let's write the result here itself. So this is theorem 6 to 11. Oh, I think I missed something in between also, because okay, yes, how can it be 11? Example 9 is not the supremum and infimum of the empty set. Example 9 is actually this. Okay, sorry about this mess up. Example 6 to 9 is this. Supremum of the set of all positive integers is plus infinity and the infimum is 1. And example 10 is that empty set. Okay, so that's why it's nice to have numbers. This is example 10. Anyway, so now the theorem is this. Let E be a subset of the set of extended real numbers. Then the following statements are true. A for every x belonging to E, we have x less than or equal to the supremum of E and x greater than or equal to the infimum of E. So the supremum of E, what we have defined, is actually an upper bound for E, and infimum of E is actually a lower bound for E. Part B. Suppose that M is an upper bound of E, that is, x is less than or equal to M for all x belonging to E. Then supremum of E is less than or equal to M. And in this context, you should understand that because everything we are doing in the extended real number system, so M itself is an extended real number. It's not necessarily a real number. Okay. Then supremum of E is less than or equal to M. So this part says that among all the upper bounds, supremum of E is the least. So that's why it's justified to call it the least upper bound. This says that it's an upper bound, and this says that it's the smallest among all the upper bounds. And just like that, there is one for the infimum. Suppose that, let's call it small m, is a lower bound of the set E, that is, x is greater than or equal to small m for all elements x in E. Then the infimum of E is greater than or equal to small m. The infimum, besides being a lower bound for E, is also, the greatest among all the lower bounds. It's the largest. And the proof of this is the second exercise. Now before we end this video, let's just see one more thing. We mentioned that this is the only case in which the supremum is less than the infimum. That means for a non-empty set, the supremum is always greater than or equal to the infimum. This one can show using part A. Do you see how? Suppose your E is a non-empty subset of R star. Okay, that means there is something in E, so you can choose that something to be X. Then you have these two things. X is greater than or equal to the infimum of E, and at the same time X is less than or equal to the supremum of E. Now you use the fact that our ordered relation satisfies transitivity. So infimum should be less than or equal to supremum. Unlike this case, where infimum is greater than supremum. And keep in mind that our order, besides being transitive, is also it satisfies trichotomy law. So once you have supremum less than infimum, then at the same time supremum cannot be either equal to infimum or greater than infimum. Exactly one of the three cases should be true. So our remark that this is the only case in which supremum is strictly less than infimum is justified by this. Okay, so once we prove this, then this is also proved. So let's end things here. In the next part, we will solve these exercises and complete the section. Now after this section, I think in the next one we see those notions of limit points of sequences, and also the very important notions of limit superior and limit inferior, or which are also known as respectively the upper limit and lower limit of a sequence. So until then, this is me, Lucifer, from a mathematical room. Have a nice night.